Hi everyone, this is Elia Carlo Zirondelli, and I will talk about our most recent result, that is a safe, complete, and linear time algorithm for genome assembly. First of all, we have to understand what genome assembly problem is. As a flagship problem in bioinformatics, it usually asks to reconstruct an unknown string known as the genome from many shorter substrings of it. The hardness of these kind of problems comes from the size of real data, as well from the errors which may come from the machines, and the formulation of the problem itself allow from equally important and multiple solutions. So how should one tackle a genome assembly problem? In practice, state-of-art assemblers first build an assembly graph that encodes the overlap of the genome, like, for example, the De Bruijn graph. And in these assembly graphs, they search for strings labeling the unitics. Unitics are paths. The internal nodes are paths that the internal nodes have in and out degree equal to 1. We don't care about the in degree of the first node or the out degree of the last node. We only care about the in and out degree of the internal nodes. Another thing to notice is that these assemblers work in linear time to find unitics. So this is a bottleneck for our result. We didn't want to pay more than linear time to find even more complex solution than unitics. In theory, one can also enumerate all solutions or even find the k first best solutions. But this is, as you may have noticed, very impractical if the number of solutions is very large, like compared to the human genome. So, the first thing to do is to put ourselves in a different framework. So this framework that we work with was first introduced in the paper that I cited in the footnote. And it's based on the definition of a safe partial solution. So given us a notion of solution of our problem, like, for example, taking the De Bruijn graph, a solution for a strongly connected graph like the De Bruijn graph is a closed R-covering walk of the graph itself. Notice that this kind of solution are already many, because if you take a closed R-covering walk for the De Bruijn graph and you repeat it twice, you have already a different solution. But anyway, given a notion of solution, a partial solution is considered to be safe if it appears in all solution of the problem. So it's already easy to see that unitics, first introduced in the previous slide, are safe walk for closed R-covering walks. With the definition of safe partial solution also comes the definition of a safe and complete algorithm. In fact, a safe and complete algorithm is an algorithm that returns every safe solution, every safe partial solution for a problem. A first characterization of safe walks in the case of the solution as closed R-covering walks also came in this paper with a definition of an omnitic. An omnitic W is a walk that has no forbidden path from any two internal nodes of the walk. So what we call a forbidden path is, first, we defined the function t and h, like the function t represents t of an arc is the tail of that arc. So is the starting point of the arc, while the head of an arc is the ending point of an arc. So a forbidden path is a backward path inside the omnitic, starting from two internal nodes. But the first arc and the last arc of the forbidden path have to be different from the arc of the walk. Like in the figure, the forbidden path P starts from tail of EJ and uses a different arc than EJ and ends in the head of EI minus 1, using a different arc than EI minus 1. So with the omnitic characterization, they also obtained the very first safe and complete genome assembly algorithm, which came around 20 years after the very first usage of Unitix in genome assembly. Omnitics, they proved that carry around 60% more biological content than Unitix. So Omnitics should play an important role in genome assembly. With very little insight on structural property of Omnitics, being them a novel kind of safe walks and a novel kind of framework to work with, they obtained only a cubic time for enumeration of all maximal omnitics. The key idea behind their algorithm was in fact an exhaustive extension of any given omnitic with every arc outgoing from its set, while preserving the property of being an omnitic. So basically, starting from the fact that every arc in a closed arc covering walk solution is an omnitic, they try to extend an arc by adding another arc from one of any outgoing edges of the arc, trying to preserve the property of being an omnitic. This required a check for every internal node of the walk for the presence of a forbidden path. This is why they obtained only a cubic time for enumerating all maximal omnitics. A more recent results by Cairo proved that the length of all maximal omnitics in a graph is indeed quadratic, is in the order of n times m, where n is the number of nodes of the graph and m is the number of arcs. They also offered an algorithm that took quadratic time to enumerate all maximal omnitics, and they proved it to be optimal, since they showed that there exists a family of graphs in which the total length of omnitics is indeed quadratic, and their algorithm was indeed optimal to find every maximal omnitic in that graph. They, however, had much more insight on the structural property of the omnitics, and I show you here two of the main properties that they discovered and that I found very useful in proving our result. The first one is to prove that there exists, and it is unique, the left maximal omnitic ending with a given split arc. So left maximal omnitic is basically an omnitic which cannot be extended to its left. So whenever we try to add an arc to its left extremity, we create a forbidden path for the walk. Split arc is a notation that I used for what they call a branch arc. Basically, a split arc is an arc that has a sibling starting from its tail node. So symmetrically, a join arc is what we call an arc that has a sibling in its head node. The most important property that they proved is that there exists an acyclic relationship between two given split arcs. So two split arcs are in relation if there exists an omnitic. Two split arcs, let's say G and G prime, are in a relation if there exists an omnitic, say G, P, G prime, where P is a univocal path, going from the head of the arc G and ending in the tail of the arc G prime. A univocal path is nothing more than a path comprised only by join arcs. So this path has no outgoing edges growing from any of its internal nodes, but it only has incoming edges. So the key idea behind this algorithm was to recursively compute, with the help of memoization, the left maximal omnitics ending with a given split arc. And once you have obtained every left maximal omnitic for every split arc, ending with a given split arc, you just have to append the longest univocal path to its right, starting from the head of this given split arc, to obtain its right maximality and hence the maximality of the walk. So in this slide, I want to briefly show how that they proved that their bound on the algorithm was indeed tight, because their algorithm took quadratic time no matter the length of the maximal omnities. In this family of graph, we have omega n nodes and omega m arcs. And the maximal omnities are, as written in the slides, of the form: first, the whole unitic G1, Gn, then any F arc, the corresponding arc of the bipartite graph, which can be any of the outgoing from the head of F, the corresponding arc of the F prime class, and then again the G1, Gn class. So in this family of graph, the maximal omnity have total length exactly quadratic. And since the algorithm took quadratic time to run and enumerate all maximal omnities, their bound was indeed tight. In these slides, I show our main result, which is a theorem and a couple of corollary. The theory basically says that there exists an order of m size representation of every maximal omnities of the graph. More formally, there exist two sets, M and F, which are respectively a set of walks of total length order of n and a set comprised by only single arcs. The important thing is that we prove that every maximal omnitic of a graph is either the univocal extension of a subwalk of a walk in M, or it's the univocal extension of a walk in F. In addition, both M and F and the endpoints of said subwalks that univocally identify every maximal omnitic of the graph can be computed in linear time. This led to two different corollary. One that basically says that it's possible to enumerate all maximal omnitics of a graph in time linear in their length. This is an important step up from the previous result because, as I said, the algorithm of Cairo had quadratic time even for those maximal omnitics that had linear length. But we improved this by having an algorithm that takes linear time to enumerate all maximal omnitics in their total length. In another corollary, instead represents an important result based on the fact that it's possible to compute the lengths of all maximal omnitics in total time order of m. This allows to have important statistics about omnitics, like in linear time, you can answer questions like what's the longest or shortest maximal omnitic of the graph, or even what's the average length of all the maximal omnitics of the graph. So in the next slide, we are going to show what are the main structural and theoretical results that allowed us to reach this result. In the paper, we consider graph of constant degree, but we also show how to obtain graph of constant degree starting from every strongly connected graph through very simple and linear transformations. Nodes of graph of constant degree are of three kinds. They can be either join nodes, and they are read in the figure, and they have in degree equal to 2 and out degree equal to 1 symmetrically. They can also be split nodes and have in degree equal to 1, out degree equal to 2. There is a third kind, and we call them bivalent nodes, and are all those nodes that have in degree and out degree greater than 2. With this classification of the nodes, we obtained the definition of a macro nodes, and we call which is indeed a partition of the nodes of the graph. A macro node is identified by a single bivalent node, which is put in the center of the macro node, like in the figure, and the set of all the other nodes that either reach the bivalent node through a path comprised by only join arc, or it is reached by the bivalent node through a path comprised by only split arcs. With the classification of the nodes and the partition of the nodes into macronodes, we also have a classification of the arcs of four kinds. We have, like we said, the join arcs, split arcs, respectively in red and in blue in the figure. We have two new kinds that are the green one and we call them cross-bivalent arcs because they actually cross the macronodes and have both the endpoints in different macronodes. Or they can also be the fourth kind, like the one purple in the figure, and we call them self-bivalent arcs because they have both the endpoints in the same macronodes. In these slides, we show two properties that I think played an important role in the paper, and they also show that omnitics enjoy very limited freedom inside the macronodes. In fact, with the first property, the Y intersection property, we proved that if we have any omnitig ending with a given split arc, let's say G, and the prefix of this omnitig ending in the tail of this split arc is comprised by first a join arc and a path comprised by only split arc, then we have that this prefix cannot form an omnitig with any other sibling of the given starting split arc. So it basically says that there are tracks for the omnitigs to run by. The Y intersection property shows that if we have two omnitigs crossing the center of a bivalent node, crossing the center of a macronodes, so we have, like in the figure, F1 G2 omnitig and F2 G1 omnitig, then the in degree and the out degree of the bivalent node is exactly 2. In addition, in relation with the Y intersection property, we also proved that if taken any incoming arc in the bivalent node, let's say F1, then there exists at most one split arc outgoing the bivalent node that can form an omnitig with the given join arc. Next, I am going to give very briefly two definitions of structures that can be found inside macronodes, the microtigs and the macrotigs. A microtig is any kind of walk that remains inside the macronodes of the form W1, FG, W2, where FG is the couple of join arc and split arc that crosses a bivalent node, and W1, FG is an omnitig, as well as FG, W2, that do not contain internal bivalent arcs, but they can have bivalent arc as the first or the last node. So we call microtig any kind of these walks, and we call a microtig maximal whenever its first and the last arc are bivalent arcs. We proved that maximal microtigs of any graph have a linear length, have total linear length, and can be computed in linear time. A macrotigs is what we call either a microtig or the overlaps of microtigs on the same cross-bivalent arcs. And as well, a maximal microtig, we call a maximal macrotig any macrotig that cannot be extended by adding any microtig to its first or last cross-bivalent arc. We, as well as we did for microtigs, we also proved that macrotigs have total linear length and can be computed in linear time. With these notions in mind, in these slides, I want to give a brief recap of the situations inside macronodes and across macronodes, and let you see how the macrotigs plays an important role to find maximal omnitigs, because they can be actually seen as tracks in which to find omnitigs. Like in the figure, I grid out the areas that represent macronodes, and the big gray nodes are the bivalent nodes that identify each single macronodes, like U, V, and W. The maximal microtigs are identified by a black bold path that overlays the arc of the graph. Like, for example, B2, F2, G2, B3 in the upper part is the maximal microtig of the macronode MV. And you can see that it's maximal because its first and last arc are two cross-bivalent arc, B2 and B3, and the F2, G2 is exactly the couple that we call the central microomnitig that crosses the bivalent node. The maximal macrotig is once we have defined all the maximal macrotic of the graph, maximal macrotic are easily obtained by overlapping and joining together every maximal macrotic on the cross-bivalent arc that they share with each other. With the relation that we talked some previous in some slides before of Cairo, that two split arcs are in relation if they are connected by a very simple omnitic, we have been able to prove that every arc of the graph is contained in not exactly, but in at most one maximal macrotic. And the only arc that can appear twice in the same maximal macrotics are the self-bivalent arcs, like in the figure. But in the case that there is an arc contained twice in the same maximal macrotic, okay, it is a self-bivalent arc, but it also appears as the first and the last arc of the maximal macrotic. So we see that macrotic are somewhat free to move around the graph, but they also have very limited freedom. With this in mind, we have been able to prove that the arc is contained in at most one maximal macrotic, but the only arcs that have been left outside these sets of macrotics are cross-bivalent arcs. So there can exist a cross-bivalent arc that do not belong to any macrotic at all. This arc would belong to a different set in which to find maximal omnitic. Indeed, we proved that maximal omnitic are either the univocal extension of a particular subbulk of a macrotic, or it is the univocal extension of one of these cross-bivalent arcs that do not belong to any macrotic at all. The linear time goal can be obtained using the following extension property, as well as a result by Italiano that allowed us to check in order of one any strong connectivity queries under one arc removal, which is exactly what we need in the extension property. The extension property basically says that if you have an omnitic starting with a join arc, and you want to extend it to its right with a split arc, you can do it if and only if that split arc G is the only arc in the whole graph that has a path from the head of G to the head of F, removing the arc F from the graph. In the figure, we see indeed a counterexample, like G is indeed an arc that has the requested path, but since there is another one, this FWG cannot be an omnitic. This is important, and it seems very easy as a property, but the proof has been very hard because once the fact was that you had to look for forbidden path for every internal node of the walk W, but now this property allows you to do one single check from the head of W to the head of F, nothing more. So to have a brief recap on our algorithm, we proved that maximal omnitics are either the univocal extension of a bivalent arc that do not belong to any macrotics, like we see in the second lower part of the figure, or it can be seen as a univocal extension of particular subbulks of macrotics. But how can we find those particular subbulks? We use a two-finger scan, like the left finger will always point on join arcs, while the right fingers will always point on split arcs. So putting those two fingers inside the macrotics, we've put the left finger on its first join arc and the right finger on its first split arcs. We already know that for macrotics construction, this is already an omnitic. So we want to try to extend it. We extend it to the right of this omnitic using the extension property until we can no more. This is already one of those particular subbulks, and we only add the univocal extension to it, and we return it as a maximal omnitic. From there, we move the left finger to the right, so to the next join arc, and we try again to extend it to the right to any split arc. And we do it until we have visited every arc of the macrotic. And remember that there are no loops inside except for the first and the last arc, which is a self-bivalent arc, and it is the only arc that appears twice in a macrotic. We do it for every macrotic. And we can return every maximal omnitic this way in linear time. To conclude, I would like to thank you all for taking the time to listen to me. And I would like to remind you that this work was partially funded by the ERC starting grant. Thank you.